Chapter 5, Eigenvalues and Eigenvectors. In this chapter, for square matrices, you'll study how to find eigenvalues and eigenvectors, similarity transformation and diagonalization, and how to estimate eigenvalues by using computational algorithms. And we'll consider applications to differential equations and Markov chains. Here we have section 5.1, Eigenvectors and Eigenvalues. A is an n by n square metric. An eigenvector of A is a non-zero vector x such that ax equals lambda x for some scalar lambda. In this case, the scalar lambda is an eigenvalue of A and x is the corresponding eigenvector. See this example. Is this vector an eigenvector of the metric? What is the eigenvalue? In order for the vector to be an eigenvector of the metric, this equation must be satisfied. So this is metric A. Now this is vector x. So we start with ax multiplication. So A is now 5, 2, 3, 6, and x is minus 1 and 1. Okay, for that one, row column dot product, so minus 5 plus 2. For second row, minus 3 plus 6. So here this is minus 3, that is now 3. So here this must be written as the vector, okay, minus 1 and 1 times some scalar. If we put here 3, then it's okay, right? So here ax is the same as 3x, right? So x is an eigenvector of the metric A, and the corresponding eigenvalue is 3, right? A, U, V are given. Are U and V eigenvectors of A? Okay. The manner must be the same. So we'll check only for V. Okay, part A. So we start with AB. Exactly the same as the last problem. A is 1, 6, 5, 2. And V is 3 and minus 2. Row and column, that is 3 minus 12. 3 minus 12. And that is 15 minus 4. Okay. That one is now minus 9 and 11. It must be written as some scalar times here 3 minus 2. That's the question. Now, but basically it's impossible. Okay, for the first one, you can choose minus 3, but for second one, it's not satisfying. If you try to match the second one, then the first one is not matching. So there's no lambda satisfying this equation. That means that V is not eigenvector of the metric A. For you, you can check it yourself. Now, part B. Show that 7 is an eigenvalue of the metric A and find the corresponding eigenvectors. Okay. if 7 is an eigenvalue of metric A, then AX must be 7X for some non-zero vector X, right? Now, so that one can be written in this way: X minus 7X equals 0, and then here we have, that is A minus 7 identity X equal 0. Right? Now here you may wonder why we put here identity. Anyway, for any X, and that is same as identity metric times X. And also in subtraction here, A is right now 2 by 2 metric, so that simply subtracting the scalar 7 is impossible. So we put here 7I, the identity metric. Okay, we'll check this one here. Before solving the problem, let's check if it's really okay. So the meaning of that one is in fact subtraction, so that is now given this way. A is 1, 6, 5, 2, and minus 7I, which is 1, 0, 0, 1, and then here that X equals 0. Right? So with this subtraction, we subtract along the diagonal 7, so that 7 subtracted, minus 6 and 6, and 5, and again 7 is subtracted, so that minus 5, and X equals 0. So here we'll check this one if it is really okay. Okay, now here we'll check it here. Okay, now AX equals 7X if X is now X1, X2, then AX equals same as, okay, the A is 1, 6, 5, 2, so X1 plus 6X2, and the second one must be 5X1 plus 2X2, right? Okay, so AX equal 7X implies that X1 plus 6X2 and 5X1 plus 2X2 equals, here 7 times X is 7X1 here and 7X2. So we move this one to left hand side. Then here now 1X1 minus 7X1, so that 1 minus 7X1 plus 6X2, and now this is X2, 2 minus 7X2, 5X1 is remained unchanged, and now that is here plus 2 minus 7X2, right? Okay, now we can express this one as a metric vector multiplication. The first one is 1 minus 7, and that is 6, and that is 5, and 2 minus 7, and then that is X. That is exactly this one. Along the diagonal, we subtract 7 here to get that one. So for this one, we can write in this way, right? Okay, now we finish the solution. How? For the augmented metric, we may use elementary row operations. Okay, so here start with minus 6, 6, 0, and 5, minus 5, and 0. And from this one, scaling divided by minus X, then 1 minus 1, 0, and divide by 5. This one is also 1 minus 1, 0, so the same. So after replacement, we can get like that. So here, from this one, x1 equal x2. x2 is a free variable, so that x2 equal x2. So here, now x1, x2 is same as x2 and 1 and 1. And if x2 is non-zero, then here the x will be an eigenvector. So basically 1, 1 direction. So there are many eigenvectors for the eigenvalue 7. But the direction is 1, 1. Pictorially, there is 1, 1 direction here, and along the line, every vector except the origin, every vector along the line will be the corresponding eigenvectors. However, they are linearly dependent. So once you consider linear independence, then there is only one vector, one linearly independent vector, right? So just we say 1, 1. So that one is an eigenvector. But you can choose some scaled vector. So there's a reason in this question we say that find the corresponding eigenvectors. Okay. The set of all solutions of A minus lambda I x equals 0 is called the eigenspace of A corresponding to eigenvalue lambda. So it starts from ax equal lambda x, right? Okay. Lambda, okay, that is the definition of eigenspace. Lambda is an eigenvalue of A, then eigenspace is a subspace of Rn because it is a null space. And for this metric, and we try to get the solution so that eventually eigenspace is a null space. Null space is a subspace. We already know that. So eigenspace is a subspace of Rn. So we can write in this way, null space of A minus lambda I. The homogeneous equation has at least one free variable. It should have the reason is here eigenvector. Once lambda is eigenvalue, then this x must be non-zero. And so that to get a non-zero solution, here at least one free variable must be there, right? So this homogeneous equation has at least one free variable. Find a basis for the eigenspace, and hence the dimension of the eigenspace of this metric corresponding to the eigenvalue lambda equal 3. That means that we have to find the null space of A minus 3i. Right? Then, and that is the eigenspace of the eigenvalue 3. Right? Okay, so let's try to form A minus 3i, subtracting 3 along the diagonal. So 1, 0, minus 1, 3, minus 3, 3, and here 2, minus 2, and 3 is subtracted, so that is 2. Okay. Okay. we have to here solve the problem. This matrix times x equal 0, so that the collection of solutions of this homogeneous equation is the eigenspace. Right? Now exactly same way we can find it. Start with the augmented matrix and here use elementary row operations. But 0 column is not necessary, so that let's work with the matrix itself. Okay, here 1, 0, minus 1. After scaling, it will become 1 minus n 1 1. Again, this one is 1 minus n 1. Anyway, this one is 1 minus 1 and 1. Okay, we'll put this as 0. Now, subtraction. So that 1, 0, minus 1. Subtraction will make 0. Subtraction minus 1. Subtraction will make that is 2. And here, this is 0. And after scaling, minus 1, okay, is multiplied. 1, 0, minus 1, 0, 1, minus 2, 0, 0, 0. Now, this is the reduced echelon form, and x3 is a free variable. Okay, so here x1 equal, from this one, x3, x2 equal now 2x3, and x3 is free variable x3, which means that x here is x3, a free variable, and now this is 1, 2, 1. Okay, so the eigenspace is spanned by that vector, and here the dimension is 1 because this is a basis and it has only one vector, right? Okay. Okay. Find a basis for the eigenspace, and hence the dimension of the eigenspace of A corresponding to the eigenvalue 2. Okay. Let's do it again. So we have to find the null space of A minus 2i. Okay, that one is subtract 2 along the diagonal, then 2 minus 1, 6. Now 2 minus 1, again 6. 2 is subtracted, and then 2 minus 1, 6. Okay. 3 rules are the same. So from this one, if we subtract replacement, then from second row and third row will become 0 rows. Okay. Okay. Here now, so that after scaling, we have 1, now minus 1/2, and here 3, okay, and then 0, 0, 0, 0, 0, 0. Okay, so x2 and x3 are free variables, and here x1 equals half x2 minus 3 x3. x2 is a free variable, and x3 is again free variable. So from here, x1, x2, x3 is now, along with x2, we have here the first direction is half, and 1 and 0. For x3, now direction is minus 3, 0, and 1, right? So the solutions will be spanned by these two vectors. They are linearly independent, so that dimension must be 2, right? But for sometimes, for one eigenvalue, more than one linear independent eigenvectors can be obtained. But for this example, you have only one linearly independent eigenvector. The eigenvalues of a triangular matrix are the entries on its main diagonal must be, right? Here, now, when we try to get here eigenvalues, then, and for that example, here now, okay, here B, for example, minus 4i, think about this one, then, now, here, that will be 0, and also this is 0, but anyway, 0, 0, 0, and minus 2, and minus 3, and 0, and 5, 3, 0, right? Now, for that one, we try to get a non-zero vector like that equal 0, then there must be a non-zero vector because one row is 0. So after elementary row portions, we can see that at least one free variable, which means that, and this system has solution, non-trivial solution. That means here the 4 is an eigenvalue, exactly same way for now 1, you can check that, and for, okay, this is the same as for here, and also for this matrix, you can do, you can check it exactly the same way, right? And once for matrix A, lambda 3, then 3 is subtracted. Then now this column is a 0 column, so that at least one free variable available after subtracting 3i from A, so that A minus 3i will have non-trivial solution, which are eigenvectors corresponding to the number 3. Right? Now 0, for this one, already this matrix has only 2, because this is 0, 2 the PV columns, this one and that one, so that here 0 itself is an eigenvalue, because A x equals 0 immediately has non-trivial solution, right? So for triangular matrices, the diagonal entries must be eigenvalues, okay? Okay, 0 is an eigenvalue of A, means A is not invertible here. Now, once 0 is eigenvalue of A, then AX, here X is non-zero and equals 0x. So it's 0. Now, X is non-zero because X is an eigenvector. So that means that there's AX equals 0, the system has non-trivial solution, which means that A is not invertible. Once A is invertible, then the homogeneous equation has only the trivial solution, right? So for invertible matrix, and 0 cannot be an eigenvalue of the matrix, okay? If V1 to VR are eigenvectors that correspond to distinct eigenvalues, so different eigenvalues, lambda 1 to lambda r. So that means that for these vectors, a vi, okay, vi equal lambda I vi. Here I is from 1 to r. But here we assume that the lambda I, the eigenvalues are distinct. Then the set of v1 to vr are linearly independent. So this means that for distinct eigenvalues, the corresponding eigenvectors is a set of linear independent vectors. So that here this will be used later in many applications. Okay. Here we have a proof. If you are interested in mathematical theory, then try to read this proof. Show that A squared is the zero metric, then the only eigenvalue of A equals 0. Okay. Now, so we have to show that if A has an eigenvalue, that means Ax equal lambda x, then the target is here lambda is 0. And of course over there x is non-zero. Now here the condition given condition is a squared is 0. So we can make here now a squared by multiplying a one more time, so that here a squared x equal, now we multiply here again a, then lambda ax, but ax is same as lambda x, so the lambda times lambda x, which is same as lambda squared x. Now this is zero metric, so that no matter what it is, it must be 0. But x is non-zero, the scalar must be 0. So we can get here lambda squared is 0. Only the possible conclusion is lambda is 0. So we finished the proof. Okay. Now we'll go to true or false problems. If ax equals lambda x for some vector x, then lambda is an eigenvalue of a. Is it true? It is false. Here, that equation must be satisfied for non-zero x. If we say for some vector x, then it's wrong. Once x is an eigenvector of the metric, then it must be non-zero. A metric A is not invertible if and only if 0 is an eigenvalue of A. We considered it is true. A number C is an eigenvalue of A if and only if the equation, the homogeneous equation, has a non-trivial solution. Is it true? Yeah, it's true. Okay. If V1, V2 are linearly independent eigenvectors, then they correspond to distinct eigenvalues. Is it true? Maybe not. And here earlier, we solved one example that has A has two linear independent eigenvectors for the same eigenvalue. Let's go back to the problem. Okay, here for this metric, and lambda is 2, but we have two linearly independent eigenvectors. This will be an eigenvector, and again this one is also an eigenvector. We can see here two linear independent eigenvectors for the same eigenvalue. So the statement is wrong. However, if you consider the opposite, if two eigenvalues are distinct, then the corresponding eigenvectors must be linear independent. The other direction must be true. An eigenspace of A is a null space of a certain matrix. Is it true? Yeah, it must be true. So eigenspace of A for an eigenvalue lambda is the same as here null space of A minus lambda I, right? So the final statement is true. Okay, this is the end of the section. Thank you.